So today what we're going to do to introduce exponential functions is I want to define what an exponential function is first, and then build on that to look at the graph, some different features of it, get an understanding of what we're dealing with, and also look at transforming the graph. Okay? Now, an exponential function is defined as a function where the independent variable x is in the exponent. Now, there's a little bit more to it than just that, but that's the basic idea of what an exponential function is. All right? Now, you'll notice here I have written here that the parent function is f of x equals a to the x. All right? Now, there are some stipulations as to what a has to be. A is, first of all, just a number, a real number. But a has to be greater than 0. It's got to be positive. Okay, it also can't equal 0, or else you just have a constant, a horizontal line at 0. But also, a cannot equal 1. All right, a cannot equal 1. Now, I want us to think through this even before we see it. I want you to think about what our domain and range would be for this function. Starting with the domain, if I have a to the x power, what could x be? Okay, all the real numbers? Anything that an exponent can't be?
I mean, a decimal or a fraction.
Can a exponent be a fraction? Yeah. In fact, if I have something to the 1/2 power, what is that?
That's the square root.
That's the square root, right? So yeah, it actually can. X can be any real number. All right. X could be any positive number, of course. X could be 0. If I raise something to the 0 power, it equals 1. All right. And it also can be negative. All right. What does the negative in the exponent tell us to do?
1 over a to the power of x.
Yeah. Okay. It says take 1 over that power. Okay. So, or 1 over the base to that power. So, yeah, any real number will work here, okay? Now, let's think about the range. Again, let's kind of break it down based on what x is. If x is positive, all right, and a is, say, like 3, what's going to happen as x gets bigger and bigger and bigger? Yeah, it's going to go up. It's going to increase, all right? We already said when x is 0, it's going to be 1. What happens as it gets to the negative side? It's going to be a reciprocal, okay? So, like if I had 3 to the negative whatever power, what's going to happen as x gets lower and lower towards the negative infinity?
Approaches 0.
The number is going to approach 0.
Okay, very good. It's going to approach 0. All right, so what would we say our range is here?
X is greater than 0.
Or y is greater.
Or y is greater than 0.
Yeah, our function is going to be greater than 0. All right, if we wanted to, for an interval, we could say 0 to infinity. Okay? And notice it cannot equal 0 because no matter how big of an exponent you put in there, or I should say no matter how far to the negative side you go, it's never going to actually equal 0. It just continues to approach it. And that, by the way, means that y equals 0 is what?
Or
and it's
horizontal.
There we go. It's an asymptote. It's a horizontal asymptote. Okay?
So what would y next lower?
I'm sorry, what, Donald?
What fx cannot be smaller than 0.
x 再小它这个也那个玩意不会定死。为什么
x 这个是负数。
因数它就可以导数。
Make sense? Okay, thank you. Yeah, and here's the thing that makes it really is that A has to be positive. So if I'm raising a positive value to a power, it's going to be positive. You know, I'm never going to get any negative values for my function. Okay? Now, another thing I want to consider here is this, what A is allowed to be. This statement here kind of breaks A into two different ranges of values. What are those ranges of values that A could be? It's got to be greater than 0, but it can't equal 1.
So that y is not equal 1 comma 0 or 1 is not equal 1 0.
No. We're just thinking about A right now. The base of our exponential. The base of our exponential has to be a positive number, but it's not allowed to equal 1. That kind of divided it into two ranges.
Okay, then that would be a bigger than 0 than less, and less than 1.
Mm-hmm.
And then you, how do you say this? You, like united together.
Okay.
It would be a bigger than.
Yeah, okay. So we have A would be between 0 and 1, okay? Or A has to be greater than 1, right? Now, those two ranges of values are what define for us whether a function is a growth function or what we call a decay function, okay? A growth or decay. Now, think about it. Which of these ranges for A is going to make our value grow? Greater than 1, okay? Greater than 1. A is greater than 1. If we were to graph something where A is greater than 1, then it's going to look something like this. Okay? It's going to be growing as x increases. Okay? We could also call that an increasing function. Alright? It's increasing overall real numbers. Now, for decay, this is when A is between 0 and 1. The reason why it's decay is if you think of like a half to the 0 power is 1, a half to the first is a half to the second power is 1/4, a half to the third power is 1/8. It's approaching 0 as x gets bigger. Okay? So in this case, if this is our graph, it's going to look something like that. Okay? It's going to be decaying, or it's going to be going down, closer to 0. Alright, makes sense so far? Okay? Alright, so let's consider our parent function with a base of 2. Okay, so we have 2 to the x here. Alright, let's graph this first of all by finding a few points here. So if x is 2, what does y equal? 4. Okay, so we have 2, 4. And actually, you know what, to help us graph, I'm going to go by halves a little bit, just to make this bigger and easier to see. Okay, so each of these marks is 1. So our grid is going by halves. Okay, so I have the point 2, 4. What's another, if x is 1, 2. Alright, so 1, 2, 0, 1. Negative 1, a half. Negative 2, 1/4. Okay? Because it's 1 over 2 squared for 2 to the negative 2. Okay? So you can see here we've got a growth function here. It's growing as x goes from left to right. Now let's observe a few of the things we just mentioned on the previous slide, but let's observe them on this particular graph. First of all, notice that our domain is all real numbers. Our range is y is greater than 0. You'll notice here though it says the intercept is 0, 1, but over here it's saying it's 0, 1 as long as, really no matter what a equals. Okay? The y-intercept, this is something that will help you in your sketches. Unless we are stretching it or shrinking it vertically, or unless we are moving it, translating it around, the y-intercept is always going to be 0, 1. Okay? There's actually another point on this graph that will always be similar, okay? And that is, you're always going to have the point 1 and then whatever a is. Okay? So guys, if you use those 2 points to kind of get you started with your graph, that'll help in your sketching. Yes?
So you just have to work into the y curve.
That's a great question. That is our y-intercept, okay? There is no x-intercept because the x-axis is a horizontal asymptote. Okay? So this is an asymptote, so we never actually hit the x-axis. That 0, 1 is right there. Thank you.
Why is 0, 1? Because we have the exponential function just go down, just don't touch the 0. So y can smaller than y.
Well, here's the thing. It's always going to hit 0
Yeah.
for the x's because our domain is all real numbers.
Yeah.
Okay? The y will never equal 0 because even if I have, notice we're approaching it as x is negative. So that's the same thing as 1 over 2 to the x, right? Even if x is huge and we have something like 1 over, 2 to the 3,000th power. That's going to be really, really, really close to 0,
Yeah.
but it will never actually hit 0. Okay? That's the idea of the asymptote. Approaching but never equal. Yes?
You said one point was 1A. What was the second point you said to use?
The 0, 1.
It's always going to be that?
The y-intercept's always 0, 1. You always have the point 1a, unless there's some transformations going on, like it's moved over or it's stretched or shrunk vertically, but the parent functions here are always going to have those 2 points.
If we don't have the transportation, so the y-intercept always is 0.
Yeah.
Y.
Yes. Okay, so that's our basic parent function. Re-sketch this, and I want you to see these kind of side by side with some others here. So we have the point 0, 1, 1, 2, 2, 4, 3, 8, 4, 16. Okay, so we have this graph here. And we're approaching that asymptote. Okay, so that's our f of x. Okay, so let's talk about this for a second. How would g of x be different? Notice our base is 4 instead of 2, so how's that going to look any different? Grant?
It'd be like if that graph was square. So, no, it'd be closer, right? But it'd be stretched vertically.
Okay, yeah. You could either think of it as shrunk horizontally or stretched vertically. Either way, it's going to increase much faster. Okay? So, now our y-intercept is going to be what? Yeah, 0, 1. But now we have the point 1, 4, 2, 16. Once we get to 3, we're up to 64, so it's way off of our graph. Okay? Also, notice it's going to approach the x-axis. It's a little hard to see, but it's going to actually approach the x-axis faster as we go to the left. Okay? So there's our g of x right there. So you notice the bigger a is, the faster it's going to increase. Okay? So now we have h of x. We have 0.5x to the x. All right, what's this going to look like?
It'll still have the same y-intercept, and then it'll just decrease towards on the right side of the graph.
Okay,
Shrunk vertically.
Yeah, it'll approach 0.
okay, it's going to approach 0 on the right this time.
Yeah.
Remember that point 1a? When x is 1, y is a half. When x is 2, y is a quarter, okay, and so on. So we've got the asymptote over here on this side. And on the left side, 1/2 to the negative 1 power is how much? 2. And 1/2 to the negative 2 power is 4, okay? So what do you notice about this graph?
Same thing, the opposite side.
Yeah, it's the same as f, but it's on the opposite side. It's been reflected, right? Okay? So there's our h of x. It's the reflection of f across what? The y-axis. Now, what is j of x here? 2 to the negative x.
It's 1 over 6.
Okay. When he's saying take this and make it 1 over 2 to the x. Can we do that? Let's think about that. It's the same as 2 to the negative 1 to the x, right? So what do we know about j of x? It's
Same as h of x.
same as h of x. All right? Yeah, these graphs are actually the same. Okay? Now I did this intentionally because I want you to see here, by the way, notice our transformation 2 to the negative x. If you make x negative, that reflects it across the y-axis, right? That's from last unit. Okay? So when you're doing this, there's actually two different ways you can get a decay model. This is a decay function. You can either have it with a being between 0 and 1, or you could also do it with a being greater than 1 but making your x negative. Okay? There's kind of two ways you could write it. They're both mathematically equivalent though. Alright? So does that make sense? Any questions so far? Alright, so while we're on the topic of transformations, let's think about this one, okay? Take a couple minutes here on your own, and we have the parent function 2 to the x already sketched for us. I want you to try to identify all the transformations in this function, okay? And then we'll talk about graphing it, okay?
Oh, God.
Alright, so let's identify the transformations first, and then I'll talk to you about how to graph some of these. Because these are challenging to get all the transformations in and graph properly, okay? So, first of all, what's one of the transformations that we had? Samantha?
Vertical stretch by 2.
Okay, vertical stretch by a factor of 2, or to twice its height. Okay, what's another one, Ben?
Reflection across the x-axis.
Okay, reflect across x-axis.
Good job. Ow, God, your hand.
Okay? Now, what else? Grant?
Shift it to the right one.
To the right one. Okay.
1 unit to the right.
And another one.
Vertical transition up one unit.
Good. Vertical translation up 1 unit. Okay? Now, here's my recommendation, because like we said, sketching these is a challenge, all right? So my recommendation to you is to start by treating it as though it's just -2 times 2 to the x, okay? And doing kind of a half transformation, and then doing the shift after you do that, okay? Does that make sense?
Yeah.
So, you'll notice here all of the points that we have on our original graph, we have, of course, the y-intercept, we have 0, 1, we have the point 1, 2, we have the point 2, 4, and we have the point 3, 8. Okay? All of those points, the y-coordinates can be multiplied by -2, because we're going to stretch it to twice its height and then flip it over the x-axis. All right? So this 0, 1, if we double the height, it's now at 0, 2, but then we reflect it down to 0, -2. Okay? We can do that in our heads decently well, all right? So we've got a point here at 0, -2. And then 1, 2, if you think doubling it, it's 1, 4. Then you make it negative, it's 1, -4. Okay? 2, 4 becomes 2, -8. And 3, 8 becomes 3, -16. So it's off of our graph. But at this point, notice we can get kind of this preliminary sketch of what it's going to look like. Okay? So now all we have to do is translate that to the right 1 unit and up 1 unit. Okay? So I always leave my transformations until last. So now I had the point 0, -2. I'm going to move that to the right 1 and up 1. I'm going to move my next point to the right 1 and up 1, to the right 1 and up 1. And there's one other thing here that we may forget about, but it's going to be translated as well.
0, 1? Oh, the second part of it.
No? What's a part of the graph that we don't really see?
The asymptote?
The asymptote. Where is our asymptote going to be?
So at y equals 1.
At y equals 1. Because remember, our whole graph is shifted up 1 unit, right? So if we shift it up 1 unit, our asymptote is also going to shift up 1 unit. Okay? So here's our asymptote at y equals 1. This is probably the most commonly missed part of this, is students still have it approaching 0, but it actually is going to approach +1. Okay? So you can see here, just kind of breaking this down into kind of a 2-step process, just lightly sketching the intermediate graph and then translating it at the end can be really helpful. Okay?
I just went for it. I made the little box with the points and just
Okay?
for it.
And that does work. Alright, so any questions? Donald?
So, what is the asymptote? Is y equals what?
The asymptote is y equals 1 because the asymptote originally was y equals 0, right?
Yes.
But the whole thing gets shifted up 1 unit.
Yeah.
So your asymptote is going to shift with that. So now our asymptote is at y equals 1 instead of y equals 0. Okay?
Why is asymptote
Well, we always do the reflection before we do any translating. It's possible to do it the other way, but it's a lot harder. So, okay?